survey research. Just touch on what's generally meant by big data and some of the concepts in there. Again, as I say, this is my point of view. Some people disagree with it, which will be good. That's what I want to hear. Talk a bit about behaviour of big data and market research, and that's a key aspect. And then some thoughts of mine about, how we need to go forwards when we're thinking of these concepts, and how this, in some ways, alters the way we look at market research. Next slide, please. For many years, market research was in a data desert. Data was expensive. It was hard to collect. For old people like me, we remember the paper surveys and all the problems of getting the paper surveys back and getting the data in and all this kind of stuff. And then we had this wonderful thing called telephone interviewing, which was an improvement in terms of speed, but it still cost a relative amount of money to get your completes. All sorts of issues about managing hundreds of interviewers. If you've ever worked with telephone interviewers, you probably want to find another line of business. They will drive you crazy. They really will. And so the whole process of collecting data, used to be very long, time-consuming, complicated, and expensive. You were hunting for completes. 300 completes for a survey. If you were in the big time, you were doing 3,000 completes. And then you got the really big long-term studies with thousands and thousands of completes, which were relatively rare because it was long, it was time-consuming, it was just not something that was terribly practical. We then had to think about all sorts of things to do with sampling. Once telephone penetration reached a certain level, and believe it or not everybody used to have a telephone, even those old landlines, then we could do all sorts of wonderful sampling, but there was still all sorts of considerations about getting it balanced and how we balanced it, and all those kinds of things. And we still had limited data. We still might be making conclusions based on 300 completes, or maybe 1,000 completed surveys, and there's a limit to how many demographics you can balance that to. If you've only got 300 completes, you can't really be saying, well, it's balanced across census and income and gender and all these kinds of things. We really have limited external validity. And that really meant, coming down to it, there wasn't much we could say because we had limited data. It was just too hard. Next slide, please. Not a very original slide of a tsunami, but this is where I claim I didn't put them in there. Then we got the data tsunami. Now, this was when we suddenly found that we could get data. Now, the questions about whether or not the data was of very high quality is a different thing. But all of a sudden, it was easier to get a lot of data. One of the turning points for online surveys was the election in the year 2000. Up until that point, online data collection had been going on for a while, but it was always viewed with slight suspicion. A company called Harris Interactive, who some of you might know of, were very big then. They were the first big online panel provider, did a lot of online work. I liked them because I sold them their software and I thought they were pretty cool. And they actually managed to do a very good job of predicting the outcome of the election at that point. And that was something that really changed a lot of people's minds. They sort of brought in this idea of propensity weighting, this guy called George Tahanian, who now works at Toluna. And they really validated it. Up until that point, online surveys were regarded with a great deal of suspicion. And I talked to some of my friends about this, and we kind of came to the conclusion that that was one of the turning points in online data collection where it became valid. So what we got was a lot of data. We could get the data all of a sudden. We weren't, worrying about 300 completes. We could go out and get, a couple of thousand completes. This was great. We had data, and it didn't cost a fortune to get. Okay, what we weren't sure that we were getting was stuff that was representative. There's another big issue. And there's all this endless debate about are people who they say they are when they're doing online surveys and all this kind of stuff. So while we got quantity, there was an issue with quality. Next slide, please. So, coming back to talking about big data, just want to talk about data a little bit. I always identify three forms of data: metadata, paradata, and data. Data is the data. Metadata is describing what the data is. Code 1 means male, code 2 means female. Paradata is data about the way the data is being collected. For instance, how quickly somebody responded to a question is an example of paradata about that question. How quickly somebody completes a survey. how where they were completing the survey. That can be regarded as paradata. And big data, as one of my co-presenters pointed out to me, really means predictive analytics. That's what we're really talking about when we talk about big data. And it means that, you know, we suddenly have data that we want to use to predict behaviour, predict outcomes. And the central dogma of big data, to my mind, is that it's kind of Marxist. The belief that historical analysis will predict the future. And that really is, you know, the core of the big data movement, that we've got predictive analytics, that we can look at the past and we can predict the future. Now, I don't know if you guys have heard of this guy called Nassim Taleb, and his book called Black Swan, The Black Swan. Very interesting book, very much worth reading. He comes perspective of being on the stock market and all that kind of stuff. And one of the things that he points out is that that's not always the case. The past doesn't always predict the future in the way that you quite expect. And I think that's something always worth keeping in mind when we're talking about big data and predictive analytics, is that there are these events, black swan events, we can all go, you know, you can read about the history of that concept, that these are totally unpredictable events that can still happen. So while we have big data, there is something to be mindful of, is that it doesn't necessarily always mean that we can predict the future, and these odd events do happen. Next slide, please. When we talk about predictive analytics, to my mind anyway, and other people may have a different point of view, we're talking about stuff to do with machine learning, that people also use artificial intelligence. That's using algorithms which aren't similar to the kind of statistical algorithms that market researchers are used to, like t-tests, which are hypothesis testing or analysis of variance. Things like that. We're going to be using algorithms and techniques that are really mimicking, in some ways, often the way we think people work, or at least producing predictive results. And they don't necessarily have many assumptions about the way the data works. A key part, to my mind, of predictive analytics is both having a system that will learn from the past to predict the future, and very often these systems are to do with pattern recognition. And if you look at human psychology and the way the brain works, we spend an awful lot of time trying to pick up patterns in things. That's what we do to behave. We classify things. We want to be able to say, well, you know, if that big stripy thing's running towards me, it usually means it's going to be a very bad day. You know, that fruit on the tree is going to be, you know, a lot better for me. And so these are two aspects of machine learning that mimic, if you like, human psychology. Next slide. I'm going to talk about, very briefly, two sets of techniques. This is very biased, I'm interested in them, and I've used them. There are a vast range of predictive analytic techniques that I think a lot of market researchers haven't really come across, because they are outside of the normal statistical analysis methods that we tend to use in market research. But they are tremendously interesting. And you know, if you have some sort of interest in statistics, I would recommend you particularly go and reading up about these two sets of techniques. They are relatively well known now. They've been around actually for quite a while. That's all right. We'll do the same a lot. Now, I put agnostic in there. Is that you can classify a lot of these techniques as non-parametric in that they don't make any assumptions. Now, if you're a good statistician, you understand that a t-test assumes normal distributions of the data, it assumes homogeneity of variance, it makes various assumptions about the data and the environment. These techniques dispense with those. They just want a set of data that can then be used to predict the future. And they have very little assumptions about what that data, its distribution may be, or the characteristics of that data. Next slide. We'll talk about neural networks. Now, as the name implies, they were developed in response to the idea that we could mimic the way the brain works, the way neurons work. And it was actually these guys called McCulloch and Pitts in 1943 who wrote a very prosaically named paper called A Logical Calculus of Ideas Imitating Nervous Activity. I just like the word imminent, it's pretty good. And they, you know, those guys said, well, look, we could build perhaps systems that really mimic the way neurons worked. And what people found, and there's been a lot of work done on these, is that you can actually get these systems to learn complex relationships, very complicated nonlinear relationships that might have all sorts of characteristics that you wouldn't be able to model, for instance, in even polynomial regression or any multiple regression or logistic regression, in that, you know, they have the flexibility to encode these kinds of relationships that are just outside of anything that normal statistics will do. And when we're in the real world and dealing with a lot of complicated behavioural data, this can be really important. Next slide, please. This is a bad diagram of a neural network. It's called, we call a feed-forward network. And the whole idea is that the yellow units here are mimicking neurons. You put data into those, it gets encoded and transformed, and the nice purple output there is the output. And there is an entire iterative process of adjusting the way that this network works. There's all these things called transfer functions. If you go on Wikipedia, you know, you're going to get more information about this than you ever want. And, you know, these kinds of, and there are a vast number of different sorts of these networks, and they will give you a predictive algorithm. So what you do is you train it, you say, okay, here's my test data set, you know, you train it up, and then you test it on another part of the data. Usually you random select two halves. And this is, has become a pretty well accepted in some fields way of generating predictions. As I say, these are my pet interests, so, you know, it is not by any means the only way. Next slide, please. These algorithms, called genetic algorithms, my man called John Holland, who started the field, I think he was working in gas thermodynamics, which is obviously, as the name implies, a very complicated set of behaviours. It's very difficult. Next slide. And he had the idea that we looked at the way evolution works. Now, I don't know of any creationist algorithms or Lamarckian algorithms, but it really is a biological metaphor for the way evolution happens. So, you encode the problem as chromosomes and alleles, and there is an entire set of way in encoding. It's really fascinating the way people can set this up. You know, sometimes you might be saying, well, okay, this is an equation that I think predicts something. When you break up the equation into different components, and then you do the process of what you would think of an evolutionary process where you cross over, you mate your algorithms. Not very romantic, but that's really what happens. You mate them, and then you have mutations, and you can mutate the representation of the equation. So then you generate a population, you know, all sorts of different examples of possible equations, and you have an evaluation. It's like, okay, how well does it predict behavior X or outcome Y? And then you score all these different forms of the equations, you take the leaders, then you mix them up again, the way evolution would work, you know, the Neanderthals go and mate off with Homo sapiens, or whoever it was at the time. And again, it's an iterative process, and what happens is that you can grow very complex functions in this way that actually work really very well. And in a lot of fields, genetic algorithms can be very, very useful where there is a very complicated problem space, where you're not sure exactly how the problem space works. You really aren't sure how the variables are interrelated. But because the algorithms don't require you to have any a priori knowledge of the field, it just learns, it'll go off and learn this stuff, you can develop a good predictive mechanism. One of the interesting things about this, and I actually did do some work using, believe it or not, GAs to do sample balancing in panel samples, essentially doing ring balancing, is that mutation isn't really that significant. It's really the crossover functions that are more important. And while sometimes people think that, you know, in evolutionary terms, mutation may be really important, what it turns out is that it really isn't that important when you look at genetic algorithms. And I think, in particular, I think this approach, my favourite approach for these kinds of problems, genetic algorithms, hold the most promise. And for market researchers, I think it's something well worth looking at. And you can charge your clients a lot of money for these. This is important. We're all in business here, and this is something where you can gain real expertise and dispense with the traditional statisticians like Chris. No, we love you, Ruth.
Not that traditional.
Well, no, not very traditional. Okay, I'll take back the tradition. And as I say, we used it in a particular set of problems where we wanted to develop an algorithm to do more accurate balancing, ring balancing on a sample, which if any of you have ever looked at that is quite complicated. This worked out really very well. And, you know, there is a very big panel management system at the moment running out there that uses a genetic algorithm to balance the sample.
Not that anything is going on at the moment where weighting might be a big political issue.
Yes, no,
not that anything.
Yeah,
you mean until 8 o'clock?
Yeah, until 8 o'clock.
Yeah. Next slide. When we're talking about market research, going back to this subject, social media data is perhaps one of the areas where we suddenly see the impingement of big data on the traditional market research world. When we're in this data desert, if you were asking somebody on the telephone, you had an interview saying, well, okay, and what else did you think about this product, X or Y, or what did you think? You very often get a one-line answer reporting the data, didn't think it smelled very nice, colour was wrong. And the issue there was, of course, was that the interview was editing. We all knew that happened. The interview was editing. The person could give a 20-minute spell and the interviewer go, didn't like the colour, go, because they didn't want to type all this text in. Social media, and particularly when we started doing internet surveys, one of the biggest differences that was immediately noticed was the length of the open-ended text. Suddenly you got people typing in these 1,000-word essays about something that before you'd only get 1 or 2 lines. And this was great, of course. It increased your coding costs exponentially because, instead of coding a single sentence, you're coding 1,000 words. And I think this is where the biggest potential and challenge could come in market research. And we're getting a lot of social media data. It is big data in the sense that we've got a lot of it. And also we want to use that data to predict what people are going to do. And text has its own set of problems. The author Gore Vidal used to say he spoke in sentences. He spoke in a very structured way. People don't, we get things on Twitter like it sucks fat or, whatever that means. I think I got that from my daughter, and quite sure of that. And we have a lot of different forms. We have text messages, which are just, very compressed. We have social media messages. You've all seen the comments on Facebook. Now, everybody perceives that these have a lot of value, perhaps. But of course, there's a problem with analysing them. You've got to try and parse them into different sections if you use a certain approach. You've got to work out what are verbs, subjects, objects. And when you've got a phrase like it sucks fat, you've got a problem. Next slide. Cuties like that. Sentiment analysis. Now, if you go online, there's actually I didn't manage to get it in the talk. There's a great ongoing analysis of Twitter feed with the sentiment analysis being pro for Obama or pro Romney. And there's going to be a lot of analytics done after this election on those kinds of social media metrics to predict. Text is messy because language is messy, and this is a big challenge now. We've got to work out how to analyse all this social media data and predict it, because it's not clear. There are 2 approaches with this: grammatical, where you break it down and you look at what the subject, object, and verb is and try and parse it, or the stochastic, where you're really doing more sophisticated word counts. The guy called Noam Chomsky, who's mostly known now for his political stuff, but before that he was known as a psycholinguist, and he had a lovely sentence which is colourless green ideas sleeping furiously, grammatically correct, meaningless. And so there's a real frontier here, and I think this is probably one of the most important frontiers for MR, of working out how to use this social media data and working out how to use it in a predictive way. Next slide. I think it's the last slide. Can we look at surveys as big data? Well, yes, we can, because we can collect a lot more surveys now. We can fuse them with other sorts of data, which could be anything behavioural, shopping interests, all those kinds of stuff. And in that respect, then, we can apply some of these new techniques, or at least new to MR, to predict behaviour. We can merge the survey data and the behavioural data. There's questions about, what kind of questions you ask in a survey. Do you ask attitudes? Do you ask what people have done? And something that, if you have a panel, you can do a whole respondent. You can take everybody's response to any survey they've ever done on the panel, and then use that to predict what they're going to do. So surveys can be big data. Next slide. The last one. So the big frontier here is turning ourselves perhaps into predictors. Rather than explaining, we predict. You know, I think Eric Smith said something about statisticians being the new rock stars because they do data analytics. Chris has got, the right haircut for a rock star. And I think MI has to embrace prediction rather than explanation. There's been, a lot of emphasis, I think, in the past about explanation rather than prediction. And while a lot of these techniques don't make any assumptions about how the data works, I think MI has to start coming up with some real theories about why people really do buy things and why people respond to surveys. That's all I've got to say. Thanks for your time.
If we go back to the Q&A round.
Yeah, we'll be doing a Q&A at the end of Anil's session. Anil is presenting last.
Okay, can you guys hear me again? Yes? Okay. So thanks to Andrew Jeffers. Now my understanding is the way we're going to do this is we're now going to bring on Chris Metcalf, who's going to give our next piece, and then we're going to have questions and discussions afterwards. Is that correct? That's how I understand it. So thanks to Andrew. Actually, and I think we're going to have a lot to discuss when we get to the question part. He said that statisticians are the new rock stars. I think he also said that Bayesian statistics is the new crack cocaine, which I think that Chris Metcalf may be able to enlighten us on. So I'd like to introduce you.
That's a tough act to follow where you're talking about Noam Chomsky and crack cocaine. So how much time do we have? So I'm Christian Metcalf. I'm VP of Products and one of the co-founders of Context Rolling. We're actually located next door. We're about an 8-month-old company, and our goal in life is to productize machine learning. And we're not productizing machine learning for data scientists because we also share the view that Eric Schmidt has, which is that machine learning experts and data scientists really are the rock stars. They command salaries that, it's not that they're insane, it's just reflective of the demand in the marketplace for what they do. And we think that there needs to be a bigger vision for this to carry on to the next group of companies that are going to essentially use machine learning to dominate their spaces. So next slide, please. So it's a little bit about Context Rolling. We've been around only about 8 months, but actually Stephen Perpura, who's co-founder of the company, he and I, believe it or not, first started talking about this about 12 years ago when I was an associate at a venture capital firm here in Seattle, and he was at one of our portfolio companies. So there's a lot of people on the team. Scott Golder, who's here as well, he's one of our data scientists and staff sociologists. We've been talking about this for quite a long time. Next slide, please. So, it's really, with machine learning, I think as Andrew said, it's really all just a matter of perspective. And it's really hard to see patterns when you're that close to it. One of the things that frequently will happen when we're on a customer side is they'll say, well, what do you think? And I'll say to them, if I could give you an answer and give you insight, then this isn't a machine learning problem. It's actually not a data science problem. In that case, call McKinsey. You get really, really bright people that'll come and give you their opinion, and you'll pay good money for their opinion. But if you want to figure out what the data says, the only way to do it is to basically go through it with advanced machine learning algorithms. And today, to operate those algorithms and to basically command them, you need a team of very high-skilled people to do it. So what's happening? Well, as the growth of data has gotten bigger and bigger, if you just keep looking and build it all the way out, that gap between data and insight is just getting larger and larger. And again, it takes sophisticated teams of people that can help you cross that chasm, simply because one of our customers once said, well, gosh, it almost seems like you need to spend 10 years studying this stuff to make it work. And the answer is you do, because the tools that have been built, if you look at Mahout, if you look at any of the Hadoop technologies. The reality is the people that are experts about this have either been in industry working on this most of their lives or have been in academia working on this most of their lives, because that's what these tools were essentially built for. So next slide. So what's one of the problems? Well, one of the big problems, and you'd be surprised, even at the companies that are really sophisticated with going about this, the reality is when you're first trying to assess what you have, so even just basic ETL, and then you're trying to turn that into analysis and modeling, and then you're trying to turn that into prediction, it actually involves different systems. Sometimes people use, I heard people here talking about SPSS, maybe use R, maybe use Stata. There's a bunch of different tools that you can do it, but the reality is each one of them have their own limitations, each one of them have their own quirks in how you import and export the data. And essentially what happens is each time you go from one system to the next system to the next system, you're having to transform the data, and in some cases you're having to rely on highly skilled people like Scott to figure out what's okay to throw out, what's okay to keep in, what's okay to throw out. And usually you end up in a situation, especially if you're a Google or a Microsoft, where you're persistently up against the edge of what that system can take. So that's fine, you found a way to make that work. But the reality is, what do you then do, as Andrew was talking about, to make your prediction better? Well, the way you make your prediction better is you add another data source. So what do you do if the systems that you're using along the way are already at the edge of what they do? The reality is you either pull out your hair, or you hire a couple more people like Scott to come in and help you basically rework the wheel and start from scratch. And that's one of the reasons that this is so incredibly hard right now. Next slide. So there's a lot of promise of big data. Lots of companies are playing with it. It's one of the spaces that the analyst firms are most excited about. You have to be wary of that. But the reality is most of the Fortune 200 are dipping their toe in the water. They're using Cloudera. They're using different Hadoop installations, Hadoop to different degrees. But the reality is that they're not getting the insights that they want, and they're certainly not doing anything that approaches real-time analytics or something where you can get in the quick stream of user behavior and either influence them or give them better choices. Next slide. And why? It's because basically it's a mess. It's all disconnected, and as I said earlier with the different systems, each time you go from one of these puzzle pieces to the next, you're having to do transformations that, unless you're really careful or unless you have a whole lot of experience, you essentially are jeopardizing the truthfulness of the data that you're working with. Next slide. So you shouldn't be surprised why this isn't working in most companies. It's a mess, and it takes a tremendous amount of care and feeding. And while I know that this group is mostly focused on market surveys, the question, as Andrew touched on just a little bit, is how do you take the bit of information you do have about the customer or about the target that you're wanting to study, and then extrapolate that in a way that you can predict either their behavior or behavior of people like them. And behavior of people like them, it's not uncommon that a large company, even a large coffee company around here, may say, oh, well, we have 5 customer archetypes. But is that really the right number for moving forward in the future? Or is that really sort of a relic of the past, where it was really hard to identify customers and to segment them in ways that you could actually figure out how to serve them? So we would say, well, that's fine, and it's good to have a high-level overview, but at the same time, why not go a little bit deeper, and why not make your customer base your focus group rather than a focus group that somehow represents your customer base? So next slide. So systems like this lead to, and we've had customers tell us, don't worry, it's fine, that it leads them to kind of an analysis paralysis, and that's because the people that these tasks are getting thrown to, they may be very, very skilled DBAs, they may be skilled engineering managers that have never let the company down for any project they've ever taken on, but when they come across this rat's nest, it's something entirely different. And again, it comes down to, have they spent the majority of their career working on those problems? And if they haven't, it's not that they're not bright or good people, it's just going to be challenging. So next slide. So at Context Relevant, we have a different view on it. We think that really to adapt and to keep up with the perpetual growth of all these data stores, you have to connect all this. You are still going to work with other systems. We work with a lot of the open source tools as well. But essentially, we give our customers one system for doing the ETL, the data assessment, the discovery, the modeling, model execution, and then most importantly, being able to iterate on it again and again and again to make the predictions better. Next slide. So INSIGHT ahead, thanks. So when you get right down to it, I don't think that this is going to be anything that's going to surprise any of you in the marketing world. you want to predict behavior. So if you want to predict behavior, first you have to model it, and you have to evaluate it. This is essentially bringing the science wheel into our daily activities, but doing it in such a way where you're getting constant feedback for what's happening. We fully believe that the first set of models produced in our system are not going to be as accurate as the 100th model that gets produced in our system. Not because the system doesn't work well, but because that's the process. The more that you run through this, the more data that you bring to bear, and the more sources that you figure out how to basically correlate to the questions that you're asking, the more accurate things are going to be. So let's give a couple examples. Scott, do you want one of these?
Yeah, sure. Thanks, Chris. As Chris mentioned, I'm Scott. I'm a data scientist and the staff sociologist at the company. And we're going to talk about some examples. I'm sure many of you are familiar with Best Buy. Maybe you bought electronics there before. They have a lot of data. They know things about the products they sell. They know things about the customers they sell them to. They know from what they've learned from market research about the demographics of their customers and so on. Lots of data, next slide, in lots of different places. There are lots of stores, lots of departments, lots of silos, and lots of data. And it can feel intractable to make all of these disparate and separate data sources talk to one another. How do you even get started? Next slide. They have to make sense of this data because this helps improve their business performance. They want to ask questions that are actually going to help them improve their bottom line. They want to know, what are our customers going to want? How is demand going to change between this quarter and next quarter when we introduce new products, put new things on the shelves? What is the demand for those things going to be like? This affects all different parts of their business, from their supply chain to logistics management to how many people they staff in the appliances department tomorrow. Next. We actually got some public data that came from Best Buy about search queries. So when people go on to Best Buy Mobile and they do searches for some product, say some new video game that's coming out, what do we learn from that about who's going to want to buy this product? A study that came out from Google showed that users are planning their video game purchases 6 months in advance. And that means that we can use search query data now to predict what sales are going to be in the future if we do it right. Next slide. Unfortunately, if you're an analyst inside of Best Buy, put yourself in that person's shoes, you have a lot of steps to do to connect all those data sources that we were talking about. You need to transform these data sets into the form required by your modeling task. You need to combine data from lots of different places. You need to do it in real time if you're doing real time. I'm not even going to discuss all of the 15 different steps that have to take place here, but they include loading data, transforming it, aggregating it, making counts, expanding it to a longer format, and then joining extremely large tables together. And this is before you even start doing any of the stuff that's actually interesting. This is just the pain in the neck stuff that you have to go through in order to do the actual thing that you want to do. You can't even ask your question until you've gone through these 14 different steps. Next slide. What we've done is reduce that to 5 lines of code. And if you can do in 5 lines of code, which will provide you the first couple of lines of code because these are regular tasks that people are going to want to perform on a regular basis. Once you get this out of the way, then you can start to do the things that are interesting. Next slide, please. All right. We like to talk about big data recipes, and the reason that we talk about recipes is because this is how you take a thing that is extraordinarily complicated to create anew, but fairly easy for the novice person to reproduce. Julia Child spent 23 years writing her French cooking cookbook back in the 1950s, but that cookbook then made French cooking accessible to millions of people who could never even dream about doing French cooking before. And we want to do the same thing for data science. Next slide. We want to enrich data analysis with layered data. So we want people like Best Buy not just to be able to use their customer data and their product data, but also to layer on top of that other sorts of data, things like current and historical weather conditions. So if there's a snowstorm or if it's unusually cold next month, what's going to happen to my product sales and how's that going to vary across categories? Census and GIS data, which stores are going to sell product A versus product B because there's more 15-year-olds in this particular neighborhood, so video games are going to sell better, for example. Or market performance or loyalty programs. These are just some examples. The list is really endless, and that means it's important to get through the mundane stuff in a fairly easy way so that you can actually move on to the interesting things. Next slide. And we talk about building models iteratively. So you saw the wheel that Chris showed in an earlier slide. We want the iteration process to be extraordinarily quick so that you can ask more questions more quickly. Say you wanted to predict the number of units sold per day of some product. As more information is added to the model, we want to make more and more accurate predictions. So we start with a dumb model. We start with mean daily sales. We know that on an average Tuesday, you sell this many units. Well, maybe next Tuesday, you're going to sell approximately that many units. Pretty easy. Then we can add things like category, day of the week, as I mentioned, price point, and then start to get into other interesting things like weather, social media chatter, and so on. What did we learn about price? We learned that customers prefer cheap digital picture frames, they prefer cheap Xbox games and Sony Vaio products. But they actually liked expensive, that should say fax machines, it says FX machines, expensive fax machines, Sony headphones, and subwoofers. So some products, maybe it doesn't pay to discount them because customers see high prices as a signal of quality, but for other things they just see it as something more expensive than they would like, and this varies by category. What did we learn about the weather? Well, we learned that on clear days, people like FM transmitters, and on warm days, they like remote-controlled toys and DSLR cameras. Whereas on rainy days, they like things like box sets and Xbox Live memberships. And you can start to tell stories about that, right? When you envision tomorrow being rainy or the day after being rainy, because we get weather reports 5 days in advance, you may be more likely to buy a DVD box set, to buy a video game membership, and so on. And these and other kinds of insights are things that we can learn when we start to layer weather data on top of sales data. Moving on, this is one of the first things that I was interested in when I joined the company. I moved to Seattle specifically to join Context Relevant. I needed to figure out what neighborhood to live in. And there are a few things that are deeply important to me. One of them being, where do I get good coffee? And we know that Seattle has many coffee shops. Some are better than others. Some are very large chains. Some are neighborhood places. I want to live near the good ones. So we started with census data broken down by census tract. And we collected some data about available coffee shops via Yelp and layered the Yelp data over the census data. And started to look at where the good coffee shops are. Well, it depends what you like. Do you like great coffee shops, or do you want a large number of pretty decent coffee shops? And so we were looking at this two different ways. So we've labeled the census tract, by where they fall in this chart. So these areas in here tend to have a large number of pretty good shops, but then the ones that are blue are, and I actually live right there, are the ones that have a couple of really good coffee shops. So we're seeing what statisticians call mean reversion in the quality of coffee shops. However, you don't want to live somewhere that's beset by high crime rates. So we laid on top of this data Seattle police reports from 2009 and then normalized that per capita by the population of the census tract. And it looks like, unfortunately, the good coffee shops are in the same places that are subject to high crime rates. So what do you do? Beg your pardon?
Caffeine effect.
Good hearing. So there's some mathematics that goes behind this, and we took it out, but we wanted to know if there are hidden gems. So every coffee shop on Yelp has a rating associated with it of, I believe it's 0 to 5 stars, and we wanted to know if there are places that are actually better than their Yelp ratings let on. So there are some places who are losing rating points because of the neighborhoods that they happen to be located in. And so we wanted to statistically correct for this, to find diamonds in the rough. And that's what we did. And that's why I chose to live about there. Next slide. And so we have, in a number of different ways, been able to layer data about reviews, about geography, about sales trends on top of one another in order to answer questions that people actually care about. Retailers care about what their sales forecasts are going to be like. People who are moving to a city care about knowing where they should live. And maybe you don't care about coffee. Maybe you care about something else. Maybe you want to know about other kinds of establishments. And these are other kinds of data we can look at. But by layering these sorts of data together, we can develop insights, and that's what we're trying to do for our customers.
Our first systems were actually worked in high frequency trading environments on Wall Street, so very transactional oriented. And the reality is that even in those environments, especially in those environments, the more data that you layer in, the better the chance of improving your predictions. And when you get right down to it, that's really what everybody cares about. When the data is large, whether it's fast moving, high velocity, low velocity, they just want their predictions to be better. For customers, the data is not particularly large. They need predictions incredibly fast. And to us, I think, Andrew, I'd agree with you that that's a big data problem, even though the data is not huge. So, any questions that the group has, or how do you want to do the Q&A?
We're going to do Q&A at the very end.
We're actually going to do Q&A at the end.
Okay.
So I'm going to thank Chris and Scott, which kind of sounds odd to say. Thanks to Chris.
You can explain why.
Explain why. So my business partner and I, Scott, Chris. So we used to use Chris and Scott. So thanks to Chris and Scott. So I'm going to pass over now to San Francisco.
Actually, we're going to take a short break.
All right, Sam, can you hear us?
Okay, so we're going to apparently take a short break. So, and then Ramel, I'm going to ask, like I say, if when you come back on and when you introduce, if you could actually run down the sponsors for this event, because I don't have the list, and then we'll pass over to you.
Certainly, but just to check, can you hear us at all?
Yeah, I lost their audio after.
Can you? All right, then we're going to go ahead and reset the Google Hangout. Yeah, we'll resume really quickly.